today I want to have a slightly exploratory class. So what do we want to show? We want to show that if a graph has high minimum degree, okay, then it does contain a graph. I mean, these things looks a bit additional, okay. Contains a k+1 connected subgraph, okay. Suppose we, like, this is the ideal thing. Rest are coming as a some sort of, right, this is hint in some sense, okay. Okay, but all I wanted to show is that every graph with large average degree contains a large k+1 connected subgraph. That's my goal. So how do you think the proof could go? Mm-hmm. That is a good strategy, and it will work in many cases. Like it may not work here, but this strategy of finding a good separator, finding a small separator if the graph is not connected, and trying to recursively look into a part which is bigger is an excellent strategy, and in many things it will work, okay. And we will see how it works at least with respect to algorithm. This is a very useful strategy to have, okay. But here what they're trying to do, okay, is one strategy is that okay, is that you essentially guess the subgraph, okay, in some sense, and you basically prove that that subgraph has all the properties desired, okay. Or let me say that if I look at what are we looking for, we are looking for is that I want to get rid of these stupid vertices which were like they were remember what we, like, our look at our counter example. Our counter example was like this, right? So some of you would like to, you know, move into the world where, like, a graph does not contain both parts. Yes? Okay, sorry. Yeah, I never wanted to use this anymore. Okay. Okay. So yeah, so all I'm trying to say, look at the example we had from yesterday, from the click and click, right? And yeah, this is what happens when you use free pens. They don't work. And that's a new pen, by the way. Is it, can you see this? 20 rupees per class then. This is what it costs. Okay. Okay. So somehow we need, so his idea was that, look, let's look into a separator and move towards the side, one of the sides, because ultimately when I have a small separator, or like, then definitely the graph which I'm trying to consider cannot be consisting of here and here, because then this is a witness that this has a small separator. So indeed it is true that this red graph, if at all somewhere it has to be, right, then it has to be fully contained here, and it is fully contained here, okay. Now imagine if we were trying to, if suppose we prove this algorithm, how will we design an algorithm? Think about it. You understand my question? Suppose I told you that such objects exist. Suppose I prove this theorem. Now I tell you that I gave you a graph with this prescribed average degree. Can you come up with an H which satisfies this property? How will you do about it? You just said, no? This is exactly what algorithm should do. Look, I may not know, that's basic difference between algorithm and structure, right? So what will your strategy should be? Okay, I first check that my graph G itself satisfies this property or not. If it does not satisfy, then there's a witness that there is small separator. Then I'm guaranteed that the H which I'm looking for is either contained here or it is contained here. Then I can separately look here and separately look here and recursively try to construct it. You get my point? So look, as an algorithm, your strategy is perfect. Like I can translate that strategy to find such an edge. Right? Now we have to somehow make this strategy into a proof that such edge exists. You get my point? You see the difference? Like for algorithm, because you're guaranteed, I find this. Like now, if I wanted to implement this, I know that if I have a witness that there is small separator, my H cannot contain vertex from the both sides, because then I can separate this from this with this. So either it has to move the left or either it has to move the right, whatever that left and right means, right? So it's a great algorithmic strategy and people use it all the time. But for the proof, we need to make a proof version of this. You understand what I'm saying? Okay, it's vague, but like as I told you, right? This is our first non-trivial theorem of this course. Okay, so let's spend some time thinking about it. There are some 15 to 20 theorems that I want you to teach you in this course. It's one of those, my first theorem. Okay. Okay, so I will try to give you a couple of proofs for this. Okay, hopefully. Okay, so I want to introduce one idea. I just want to write it down, and then we will spend some time thinking, why did someone come up with these kind of statements? You get my point, right? Like sometimes we have, so the way I have seen it, like if I wanted to have some structure, so I generally, one way we have, okay, suppose this exists, among all those solutions, take the one which satisfies this property. Among all those, take the one which satisfies this. So you have a different priorities set, right? So first you say among all the, look at the objects which is the smallest or largest. Smallest and largest could mean either vertices or edges, vertices plus edges plus connectivity. It could be anything, right? So it's up to you. So basically you are defining some potential or some measure to the world where you are looking. And now say among all these objects in this world, I am going to refine ourselves and look into those which satisfy some other additional property. So now you have this world you made, and now you can have third priority or fourth priority or fifth priority and refine and get to something smaller which is more tractable. Okay. One other approach which people took in is that look at the smallest counter example, right? Okay, and we ultimately we want to say what is one way to prove it. One way to prove something is that there is no counterexample to this, right? So if I can show you there is no counterexample to this statement, it means I have also proved this statement, right? So what people do, let's look at a counterexample of certain size, certain this and that, and ultimately, oh, if this is your counterexample, but then this cannot happen. So this is a contradiction to the kind of counterexample you started with. Okay, and then you end up showing that, oh, it just means that there is absolutely no counterexample to my statement, right? So there are several ways of proving things: showing no counterexample, showing induction with a huge amount of additional strengthening. Otherwise, and why do you do induction with additional strengthening? Because in induction hypothesis, the object which you want to look, which you want so that you can patch things up. If you don't assume these things, then you don't know how to patch this up. So you try to prove something more stronger. Okay. Okay. So let's get into the proof. Let's make one proof first, and then we'll move on the second proof. Rest everything in this chapter are easy stuff. Okay. Okay. So this is proof from this term. Okay. So what are we going to set? So let's set gamma Can I say this is at least 2k? Because average degree is at least 4k. Then I claim that, remember, what was this? It was, like, what was the definition of epsilon g? Was by v, right? And what is, which is half of dg, right? Because dg was like you sum all the degrees and divide by 2. So this is why. And now what is an average degree is 4k, so epsilon g is at least 2k. Okay, so this is okay, good. So we have started, so we have fixed this epsilon g, which is gamma, and what I'm looking for. Okay, now I'm saying consider the subgraph G prime subset of G. Okay, so we are going to consider a subgraph G prime subset of G. No, because we say at least 4k, right? Right, greater or equal to 4. Consider the subgraph G prime subset of G such that some property are satisfied. Such that A, number of vertices is at least 2k, or I can also write this, and B, number of edges in G is strictly greater than okay. So I want to consider the subgraph G prime subset of G such that some property will be satisfied, and then we will ask, oh, among all these subgraphs that satisfy this property, we will pick the one which has some property. But first of all, why such G prime does exist? Okay, so what is the first question we should ask, right? So anything we want additional property or something, first we have to ask why such G prime exists. Why such G prime exists? Can you tell me? You understand my question, right? We say, right, consider the subgraph G prime subset of G with this property. Number of vertices is at least 2k, this. So what will the trivial, like, what will the most obvious way to show this? I think this was my water, no? Okay, fine. No. I said this was my water. Doesn't matter. Okay. Either way. Okay. So why such G prime exists? Gamma is gamma times. Gamma is a number. This number times this. Number of edges is this number times this much. Okay. Why such G prime exists? I will let you think for a minute. Do you see any such G? What is an obvious choice? Yeah. So let's see if G has such property, no? Okay. So what about G? Okay. So first, is the number of vertices at least 2k? Because look, the guy has degree at least 4k, right? So this is definitely true. Okay. So clearly, okay. And what about, is this, now you have to show this is what I have to show. Is this true? Huh? Why? Arey bhai, tell me. What is V? Hmm? V gamma. So gamma is this. So this into this is H, right? So this is equal to k times, why is, what are we saying? Number of edges is more than, is that fine? Right? Number of edges is at least, but look, it's a strictly greater inequality. If I put k equal to 0, right? No? What? No. All I'm saying is this. Graph could be 0 connected, right? Then what is he saying? You just find a k plus 1 connected, right? Then just pick up any connected component and that should satisfy this property for you, right? Look at any connected component that will satisfy this property for you. Which property? Yeah, all I require is that one connectivity, right? Then you look at any connected component that satisfies one connected, and because minimum degree is this much and the connected, so every property is satisfied, right? So we can assume, so this is exactly what I mean to say, that you see this, so we can assume that k is greater than or equal to 1 in our case, right? Because for k equal to 0, this assertion holds vacuously. Okay, so now we are in the good case. K is greater, and if k is greater than or equal to 1, then whatever it is, I mean, you are subtracting something non-trivial, so the number of edges is strictly more than something small. So there is indeed a subgraph which satisfies this property. All well? Okay. We will see. We will see. This is exactly what I'm saying. How experience, understanding, right? Because G is the one which has satisfied these two properties. So in particular, I could take in G prime equal to G. I have never said that G prime cannot be G itself. Imagine when I get a graph G which is already very highly connected, why do I need to do any of these things? Okay. K equal to 0 does not mean the graph does not have any edges. No, look at the two, look, yeah. So this is a graph with 0 connectivity with very high degree. So, yes, this, yes. But then where do you get OK equal to 0? Yeah, single vertex. If you go into those kind of pathology, you're dead. Don't. Okay. In graph theory, you first deal with general, pathology we will deal with later. If not, we will exclude them from the statement. But they are not making my statement anything interesting. Right? So in the worst case, I can do every, like, some connectivity I would have added. I could add any of these things, but like, fair enough. Okay. So now we know that G exists. So now what I'm going to take is, let G prime be the smallest subgraph. Okay, let so among all G prime, take the one with smallest number of vertices. Okay, call it H. Okay, do you understand the point? Okay, so now we know that G prime exists, and now why H? Okay, so look at his look at. So the point is, smaller something is, right, and lots of edges are there, more compact, it's more harder to break them up. I mean, there's an intuition. Okay, so why did I not take the largest such subgraph? Because think about it, I could have taken the one, the property satisfied is largest, but that is G, which does not satisfy the property, right? So now I'm trying to take the object which is the smallest one and which satisfies these two property, and I want to say what goes wrong if I take this, and the proof exhibits. So look, nobody knows what the right statement should be. You understand? Nobody knows what the right statement is. We believe something of this nature is true, and now we are trying to get a kind of proof, and based on that proof we make our statement fix. It's not the other way around. It's not that I make a statement first and then I go and prove. Okay, so first I see what seems true, then I make a statement, and then I try to prove it formally. I'm not able to because of certain cases or certain situation. I go back and rephrase my statement. I change my statement. So it's an iterative process. So like what you are able to prove or come up with, you keep on making your statements changes. Right? I'm teaching, that is why I know this statement. But suppose I did not know this statement and I want to prove the fact that if there is a large minimum degree or large average degree, then it has a large induced subgraph. How will I come about it? Right? So I believe this statement is true, then I'm trying to make some things to my proof so that I can come to the right statement. You understand my point? So it's an iterative process, and that is something more and more you play with small exercises, you will start to, those things will start to emerge. There is no, let's say, fixed palette to do that. Okay. Okay. That's all well. So now we will focus on this H. Okay. So like, first of all, H has this property, this property. Okay. First, let's ask ourselves, can H has size exactly equal to 2k? These are simple graphs, by the way. Okay. So let's see how many edges are there in H. This is at least gamma, which is at least 2k times k, right? Because H has size exactly equal to 2k. So G prime minus k, so k. So the number of edges, how many number of edges this graph can have? 2k choose 2. And we say that 2k choose 2 is greater than 2k square. Is it true? No, right? Because this is like 2k into 2k minus 1 divided by 2. So this is like 2k square minus k, and this is 2k square. So definitely, so now I'm trying to say, look, I look at the smallest guy, but how small is the smallest guy? It is definitely not equal to 2k, right? Okay, so let's write down what all things can be proved about H. Okay, so we'll write down here. Okay, call it H first. number of vertices in H is greater than or equal to 2k plus 1. It is not equal to 2k. That's the first thing. Okay. What is the minimum degree? As I told you, right? And just among all those, what if I claim that the minimum degree of H is greater than or equal to comma. Is that true? Right? If else, if there exists a vertex, if there exists a vertex V such that degree of V is less than or equal to gamma, okay, then what is the property of H minus V? Right? What is the property of H minus V? Now we know that the size of H is at least 2k plus 1. This is why we proved this. First, we know the size of H was at least 2k plus 1. If it contained this vertex, then H minus V, okay, had size at least 2k, okay. Because look, now we are making an operation on that. So we have to show that that operation satisfies this. That's the first thing. And secondly, how many number of edges in this, right? But that is like number of edges in H minus V is greater than or equal to gamma, right? H minus K minus gamma, which is equal to gamma H minus 1 minus K, right? Which is perfectly fine. So, what can I assume because of this? So, this is basically the same. Look, if average degree is very large, then a vertex which is flipping degree has no meaning. Okay. So, what the second property did we prove? We proved that the minimum degree of H is strictly greater than gamma. Okay. So, this is our working board and that's our property board. Okay. So, we proved these two things. Okay. So, there are some, so it has a high degree, this, okay. Okay. Now, this also implies what? That the cardinality of H no, because like minimum degree, so this plus 1. Okay. Now let's do something to the inequality. Okay. 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 No, I will need to use this. So no. Okay. So now what inequality our H satisfies? Our H satisfies the number of edges in H is at least gamma times, right? This is the property which is satisfied. Let's divide H from both sides. Divide the inequality from, what do we get? What do we get? Tell me. Hmm? Correct. So by definition, this is equal to epsilon h, right? Basically, I want to see how many edges are there per vertex. And what is this? This is gamma 1 minus k times, right? Is that fine? So what can we say? Can I say this is gamma minus gamma? Is this fine? Now what I know, look, mod h is larger than gamma, right? So I can say that's fine. This is fine, there's nothing wrong. So this is, yeah, I think, yeah, this is fine. Maybe there should be equality here because it could be, yeah, doesn't matter. Something. Okay, fine. So we know that every vertex is this. Now I want to prove that H satisfies. So I have made sure. So third thing what we proved here is that average degree, not average degree, vertex per degree is greater than equal to gamma minus k. Okay. So this H has lots of nice property, right? So this is what, oh, I chose H. Oh, this H is so nice because this is there. Oh, this H is also nice because of this. Oh, this H is also nice because of this. So on and so forth. So we started to add, like, see more additional structure on this H. Okay. So now the only thing which is left to prove is that it is highly connected. Okay. And now you will see why did we make these assumptions all along. Okay. So what has happened is that we have made in a way the density in such a way that, look, like both sides are more or less sufficiently dense and balanced, whatever it is called, so that if you have this kind of little separator, then you can't have too many edges per vertex, average degree, and those kind of things. Okay, you will see in a minute. Like the proof will what do you call this? So what is the meaning that this graph is, okay, what is the meaning that this graph is not k plus 1 connected? It means we have a separation a comma b such that the order of separation is at most k, right? So this is why I left the definition. Okay, so let's just focus on this. So what should I rub? Is this fine to rub this part? Because this is just, we have collected all the information there anyway. Okay, so suppose H is not k plus 1 connected. What does it implies? There exists, right? There exists an a comma b separation of G. That's it. Okay, so let's draw them picture wise. Okay, now look at, let's call this piece H1. Let's call this piece H2. So by definition, what is H1? Is A graph induced, sorry, H1 is H induced on A, H2 is H induced on B. That's it. So this is what I mean by H1 and this is H2. Okay, so can H1 satisfy these two property or H2 satisfy these two property? Because if they did, then they are smaller than H. If H1 satisfied these two property, then H1 is smaller than H. Then that is not the H we should have been looking for. We can make a same statement about H2. Okay? Okay. But before that, let's try to show something interesting. What is the size of H1, first of all? I said this is what I wanted to show to you, right? That I cannot take, look, if it satisfied both the property, then something will happen, right? So which of the property it violates? We don't know, right? Look, I said if H1 satisfied both the property, then then this selection of H was not appropriate. But first now let's go on and see which is the property it must violate, right? So first property that is, so let's say if H1 is of size at least 2k, if I can guarantee that H1 had size at least 2k, then the only thing which it can violate is the second property. You get my point, right? If out of these two property, the H1 and H2 that we have considered satisfies one property, then the only property that it can violate is the other one. Okay, so let's just prove. What is the size of H1? Can someone prove to me? Pick up some vertex here. No? Where are his degree? Hmm? Look at a vertex V here, not in here. So where is V? V is in A minus B. Here. Where are his degree? Where are his degree? His degree are here, or his degree are here. But his degree is not here for sure. And because we have a proper separation, we know such a vertex V exists. So what is his degree? Huh? Why? It's gamma, right? So we know that degree of V is more than gamma, which is equal to 2k. So degree of this vertex is at least 2k. So what is the size of H1? Is at least 2k. Similarly, I can say that H2 has size at least 2k. So now you tell me, okay, so now I say, why did I not take H1 as a subgraph that satisfies the property I desire? Well, H1 has the desired size, okay. It's just that the number of edges in H1 is strictly or less than equal to this property. Am I right? Make sense? Okay. Okay. So since H1 and H2 had size smaller than H, okay, and they are not selected as H, what does it implies? Implies that number of edges in H1 is less than equal to gamma times H1 minus k. Agreed? Number of edges in H2 is less than equal to gamma times H2 minus k. Right? All good? What? I do not understand what your question. Yeah, that's a contradiction. No? That's exactly what we're getting there. That H cannot have such separation. If H had such separation, then it has some implication, which implies that H cannot have such separation. Okay, then we will focus on the proof. Okay. Now I have done this. Okay. Okay. So, okay. Edges in H is upper bounded by H is this true? Right? Look at any edge. Either it is in this graph or it is in this graph. It's not that there is an edge from here to here. theorems, right? So every edge is either present in the graph H1 or it is present in the graph H2. And you just now showed to me this is gamma times H1 minus K plus gamma times H2 minus K, right? Which is equal to gamma times, okay, this is H minus K. Is that correct, right? If I sum this up, it's H1 plus H2. This portion will be counted twice, right? So is it fine? H minus K and minus K, or I'm doing something garbage? No, no. This is what it is, right? Look, if you compute H1 plus H2, this is upper bounded by, this quantity is upper bounded by K and this quantity is counted twice. So mod H plus K, upper bounded by mod H plus K. Is that fine? What does this contradict? That H we started with at this property. So what is the bottom line? Yeah, that we all understood. But what happened? Yes, we proved this is a formal proof. But what happened? So we try to make it proof using induction. Maybe it will be a bit more illuminating. What? I didn't get your point. If we try to prove something using induction, no. What you're trying to say? Hmm. I have tried to come up with a proof which is constructive. Okay. No, this proof is also constructive, by the way. There's nothing non-constructive about it. How will we find this proof? How will we find this proof? What's a good time to find such an algorithm? Can you come with a linear time algorithm to find such an edge? Okay, almost small number of max flows. And yeah, first we have to check the graph connectivity, right? That we can do very easily. Right? And if we have good balance separator, then we might be making good progress. But I could have that, like, I just cut off a little bit this, so I know. But notice, every iteration, right, we are making some progress. Okay, anyway, so how do we, so you get my point, right? It appears that this algorithm is constructive. When I say constructive, so we wanted to find a good graph with large degree, we deleted a vertex. So we gave the proof for algorithmic, constructive. Okay, but here it says, look, find an edge which satisfies these two properties, and among all those, find the one with the smallest cardinality, and that's your answer. Should we try to do what happened to our counter example? What fails? Huh? For what? No, I never. I said what happened is that the proof, what does it? You start with a graph and you are trying to find a subgraph that satisfies these properties. Okay. And among them, you want to find the one with the smallest size. I mean, a priori, there is no reason to believe that you will be able to find this in poly type. You might be able to find some other subgraphs that satisfy this property. But if I want you to give me a subgraph with the smallest cardinality, I'm not so sure that we will be able to do this in polytype. But P might be. It's a question to, explore. I have no answer to that. That's all that I'm saying. Look, whatever algorithm we have been discussing is to find a subgraph H that satisfies this property. But if I ask you two questions, give me a H inside this of the largest size that satisfies this property. That's a very valid question, no? Give me a H with the smallest size. That's still a valid question. I do have an algorithm. Write down these problems. Maybe we can look into those at some point of time. No, so there are two questions. Can we find an algorithm to find any such edge that satisfies this? That's a very different. That most likely is a polytype. But if we want to optimize the size in either way, I am not so sure that we should be able to do. But we need proof for this, right? Either way. Input is a graph G which satisfies this true property. A graph G with average degree at least 4k. That's your input. That's it. If it is. But if this graph is not k plus 1 connected, then you have to find the induced subgraph H, right, of largest size that satisfies all these properties, right? Agreed? Yeah, G just satisfies that it has an average degree at least 4k. That's it. That's all that it satisfies. I don't know of algorithm. Like I've never thought about it, so I cannot tell you a priori. Okay. Now I want to try one inductive proof for this, the same statement. Okay. Now let's not worry about this statement. Okay. This was given to us as a help in some sense. Okay. Okay. So for us, so like we want to prove this. Should I rub this? It was a nice proof, okay, but it was not an eliminating proof. Okay, so I want to assume for my proof. So we know how to assume k is greater than or equal to 1, right? Because if k equal to, can I assume that k is greater than or equal to 2 in a simple way? Okay, and I will say now, what is the definition of k connected? Let's say what people prove, like have to check what is the definition of connectivities are. Okay, yeah, k connected means, okay, so whatever we can prove, we'll try to prove. Okay, as I told you, it's an exploratory proof, not something which I've looked into. Okay, so how will we manage k equal to 1? If graph is connected, say if just graph is connected, then you want to find a subgraph which is at least 2 connected. If average degree is at least, okay. So what will be the assertion for k equal to 1? K equal to 0. Suppose I told you that has every graph say has 4 into 1, right? That's k equal to 1, right? And then you have to show me that it has two connected subgraphs. What is it? If every graph has minimum degree 4, it means there is a cycle. Take that cycle and that is your two connected subgraph. Done. Okay. So k equal to, and it's done, right? You get my point? That's it. Because every graph with minimum degree 2 contains a cycle. So there is lots of slack here. Think about it. Okay, excellent question. Then find a subgraph with minimum degree at least 4 and find a subgraph. Yeah, that's a good point. Right? Here's a very valid point, right? So he says, but it's an average degree. Now I'm not assuming any of these things. A graph average degree is at least 4, okay? So average degree is at least 4, which implies that there is a subgraph with minimum degree 4. In that, if a graph has minimum degree 4, it means if the graph has minimum degree 2, it means it will contain a cycle. How? Start with a vertex. Always explore a new vertex. Eventually we'll come back to it. That's a cycle. Okay? So we can safely assume that k is at least 2. Okay. Now, okay, okay. So what happens is that, okay, so let's try to apply induction, okay? Okay. And we will try to apply induction on n, the number of vertices, okay? Okay. So because of average degree condition, what two things do we know? N is at least 2k minus 1. In fact, n is at least 2k because of this average degree condition. And secondly, how many number of edges we have? N is at least something. Okay, we'll worry about those something, right? Now I'm going to apply induction on n. Okay, okay. So suppose n is like 2k minus 1, then what happens? N is y is 2k minus 1. Think you just now answered my question. If a graph has average degree 4k, then there exists a subgraph of minimum degree. So how many vertex that should contain? Imagine I have a vertex with minimum degree 3. How many fingers do I have? Here, how many fingers? 3. That's it, no? So if I have a vertex of minimum degree 2k or 4k, then look at that vertex and look at its neighbors. That itself will constitute 4k plus 1. So that's it. It is like my fingers. There's nothing more than that. Okay. Okay. So do you agree, right? This is exactly, so this is what you said, that always remember, convert your average degree to a minimum degree. Average degree is just written to make the statement much more nicer or with much more weaker condition. But intuitively, you can just assume there are. So when you are really making your proof, don't look at your average degree. Think that the graph has minimum degree 4k. Can you come up with a statement? If you can prove with this stronger assumption, then you will be able to do something with this. Right? We just now did, right? Oh, he was right when he said, oh, but how did you say that there's a cycle? This is the average degree. Oh, then we went to a component with a minimum degree and we argued there. So this is a very general recipe of going from average degree to a minimum degree. Okay? Don't forget this recipe. This is our first lesson of this course. Okay. Now I want to apply induction. So what happens if n is exactly equal to 2k minus 1? How many edges do we have in this graph? You will see something funny happening. Okay, so let me write down m is at least, for our purposes, Okay, let me write it down just for your. Okay, so you are right. This follows from the fact that average degree of a graph is greater than equal to. Okay, so let's say y n is greater than equal to 2k, since n is greater than equal to maximum degree, which is at least how much? Okay, is this statement true? If a graph has average degree 4k, then I claim there is a vertex of degree at least 4k. Average argument, right? So if a graph has a vertex of very large degree, so this is another argument, right? So if something is average, I can also say there exists a vertex of degree at most 4k, there exists a vertex of degree at least 4k because of the average argument, right? So just that, okay? So it also follows from this. You get point? If you're summing the 5 numbers and there is some average, there will be some number which is less than the average, there will be some number which is greater than the average, okay? Okay, and what is m? M is like half of average degree times n, right? Which is greater than 2k times. This is like if you do this sum. This is on purpose written for the proof to hold. Otherwise, okay, it will help us in computation. But basically, it is saying that we are going to apply induction on n. Then notice the number of vertex in the graph is this much, number of edges in the graph is this much, because it is more than 2k. Okay? There's nothing more I have written there. Okay. So if n is equal to 2k minus 1, then what is k? Is n plus 1 by 2. And hence, what is m? M is at least, how much is m then? See, 2 say 2 will get cancelled. So it is n plus 1 minus 3. So it is n minus 2. Do you agree? And here, I think I am getting this. Is that okay? Right? I substituted k equal to n plus 1 by 2. Right? Then you will get exactly this. And this is equal to half times. Is that fine? So what is this graph? Let's see. Huh? What is this? Yes, m is more than this, right? So basically, our graph is a clique. So what is G? It's Kn, and it is contained inside where? Right? Yes? Yeah, this number. I could have, because this is slightly easier to handle for us. Okay? This number is rightly chosen. You could also have played with 2kn, but the maths computation will become unnecessary, clumsy when you try to do. So I just simplified it and wrote some number which is actually smaller than 2kn, but that is bit more useful for our mathematics, or like cleaner for mathematics, nothing more, right? So the right thing would have been to just start with 2k, but like then you basically ended up doing lots of computation, getting this all the time and doing some substitution. So it's better that just assume that. You understand my point? This is convenience. This is, but basically you're going with, yes? Exactly. It is just to, so our assumption is the number of edges is at least 2kn, right? We have so many edges and this number is less than this number, right? But I wrote this way so that it is easier for us to do, see, these kind of maths. Yes, Mihir? Yes. 2kn. So what do I do? I'll get, yeah, n into n plus 1. Correct. Yeah. So this is why we can assume that n is very large. N better be very large, right? So remember our first proof, right? We say that n cannot be equal to 2k, right? We have already seen these kind of parts of the proof. So I just wanted to show to you that what happens when n and k are purely related to each other. Basically, then you are getting hugely like huge clicks kind of objects. Okay. Now you look at the proof which we had when we are doing. What are we getting into? We are getting into an induced graph or subgraph where n and k are largely related with each other, right? So those are like kind of click, not like click with like the what we did. It is not a click. I mean, it's far away from the click. It does not contain more than half the edges of a click, right? You get my point, Mihir? But you're right. All this tells us that n better be large. Okay? All these equations or whatever you want to say, it all tells that in this case n should be like at least 2k plus 1 or something minimum if you want to make any sense of this graph. Okay? But since I'm applying induction on n, right, I'm just trying to say that look, for all the base cases it is trivial. You get my point? Right? So all I was trying to show that these base cases up to this is trivial because you get click. Okay. Okay. I don't know whether we will. Okay. So now notice, if there exists a vertex V such that degree of V is less than or equal to 2k minus 3, okay, if there exists a vertex V with at most 2k minus 3, then what is the property of G minus V? Okay, it satisfies all these properties, right? So our, like I'm saying, we are saying that a graph with at least this many vertices and this many edges contains this. Okay, and basically the way it is set up is like at least the proof is set up not for k plus 1 connected subgraph but for the k subgraph. Okay. Okay. So all we can assume, if this would have been the case, we would have applied. So look at this case, right? What are we saying? I said if there is a vertex which does not destroy our premise, delete it, I have an induced subgraph with a smaller number of vertices, and hence by induction hypothesis, it does have such a subgraph and we are done. You get my point? So if I start with a graph with a small degree, I delete it and say, hey, look at this graph, it satisfies both the number of vertices is large, number of edges is large, okay, and hence it has all the property. Okay, or in other words, what are we trying to say? So we are basically saying that look at a graph G, if I have a small vertex and if we are proving by induction such that after deleting this average degree does not change it, then look at that subgraph that it has a smaller number of vertices, so you're done. You get my point? So this is an iota of the proof. So what is an iota of the proof? Like irrespective of what numbers I write, right, is that I started with a graph G, and now we are trying to do induction. If I find a vertex V which does not change my average degree, or does not change my average degree after deletion, what do we do? Delete it, apply inductively on this. Okay. Right? So that's my idea. All these numbers and everything is for maths to go. But what is an idea is that look at my graph. If there is a vertex which I delete and my average degree remains the same, like, okay, then that's a good vertex to delete. Inductively, that object has an answer, and we have done the base case, right? So that's a good vertex. So what does that allow you to assume? Now you are in the graph where every vertex has a large degree. So that is now why we need further to prove, because the kind of counter examples you had, they all had every very hard degree. So we need something more to finish our proof. Okay. Okay. So let's. What? No, what you are saying? Come again. Hmm? Yes. Less than the average degree. No. No. It could increase, because all I'm saying that average degree is at least some number, right? So all I have to show that. So you get my point. So now what is my flow? So what is an induction proof? Okay. So induction proof is we have a base case done. Okay. Okay. I will let you finish this proof because we don't have time. Second, average, like remove vertices of a small degree, because it is proved by induction. Average degree does not change, and hence we can do this inductively done. So now third, what is this? No small degree vertex. What is a no small degree vertex? We have no small degree vertex. But so minimum degree of graph is at least 2k minus 3. So either we are already done, or we have a small separator, like we have a separator of size k here and here, right? Now again we can do our edge counting business, and we will be done. So you don't have to assume that such a edge always exists, right? So what were the basic arguments? Argument was, first, if you recall, we assume that the h is large. Okay, so that forms our base case, right? Okay, why is this guy assuming h is large? So if I try to do inductively, so now if I try to do inductively, then up to h is large, it's my base case that needs to be handled. What was the next case they were saying? Oh, h has large number, so that is done. Now, oh, it has a large minimum degree. Oh, why are they assuming large minimum? Oh, if I delete this graph has a small number of vertex, inductively we are done. Okay, fine. Oh, what was the third case? Oh, now every vertex has a large degree. Fine. If every vertex has a large degree, and if it is the connectivity remains the same, again great. Otherwise, I have a small separation. Now this graph had far too many edges. So now imagine yourself that every vertex has degree n and this, right? But when you say that the number of vertices and this gets correlated, then the clique kind of situation would not arise. That's all that is happening, right? You can't find us. So my point is, like, this is why you are upping 4k. Okay, now I can do the proof if you want, but it is no more than whatever I did before, right? So you look at this separation, you count edges here, right? Because of minimum degree, there's a vertex here. You will count some edges. You will count some edges here, right? And then you please sum them up. That's it. Do you get my point? Okay. So, okay. So suppose you had such a separation. Okay. Suppose you had such a separation. Okay. Let's call this H1. Okay. I'm not doing as formally because it's just a mimicking of the earlier proof. So, okay. So let's try to see. Okay. So what should be your proof strategy? Please tell me. You will look at this vertex. Okay. How will you claim that the number of edges are small here? You will say, look at this proof, this guy. It has this many, because of minimum degree, it has at least this size. Okay. Now, if it also had that many edges, then by induction hypothesis, it contains strictly less number of vertices. And hence, such a subgraph exists and you are done. You get my point? No. So look at the separation. So we have a separation and we have a left side and a right side. Okay. Now look at a graph H1 as left plus separation. Okay. Your H2 graph is right plus separation. Right? Now look at this. It definitely has at least 2k minus 1 vertices because there is a vertex of degree 2k minus 1 hiding because of the minimum degree argument. Now if it also satisfies the number of edge requirement, then this graph has one less vertex than my original vertex, and it's satisfied by vertex requirement and edge requirement. Then by induction hypothesis, what can I say? We get them. Similarly here, right? So why did we fail? Is both here and both here. And then now you can do the counting. No? So this is how you converted that proof into an inductive proof, right? Is this constructive? Okay. And now look at that guy's proof, right? This is what we did in the, like now I basically converted what he said, right? Oh, let's look at this, and I know the solution is either going to contain inside this or contain inside that, right? So before I could apply his proof constructively, this is what I did, right? So this is what he said, that oh, you find a small separator, then go here, fine. But this is exactly what we are doing inductively, right? So, but now what are we saying? Oh, if you can't go here, then this is your answer. You can't have small separation, you're done, right? So basically what it tells us that look, if you have a small separator, then you have a direction to pursue, right? At least one side is big. And how did the B decided big? Big is the number of edges. So follow. Why can't I go both sides, right? So like, and we define like, so now big could also mean number of vertices and number of edges. So we made one thing standard. Its n is slightly larger, and if it has lots of edges, then you have satisfying the property, right? So but proof is exactly the same, right? Now this is more intuitive proof than the other one, right? Because this proof makes sense in the sense that look, if you start to make your own proof, first thing what will you do? You will get rid of small degree vertices. That's very natural, no? Because those are like thorn, right? Because look, if you're looking for a graph with connectivity some 4k, what will you do with a vertex of degree strictly less than 4k? You tell me. Is there of any use? If so now I can't do this because, so now there's a gap, right? You see, there's a gap between what connectivity I'm preserving and the average degree, right? So I allow myself to delete, so I'm adding vertices much more than the connectivity. Think about it, the gap. Look at your click. What can I prove? I couldn't, because there are 2n vertices, right? Degree is like n. There are 2n vertices, but what is the degree? Is n only. You get my point? But in our situation, what are we saying? We are saying, look, now there's a gap between the connectivity I want, right? So for example, if I asked you, oh, this graph is not connected, but if I asked you, is there a connectivity of n connected subgraph? Then you can find it. No? Look at your click example and say, give me an n connected induced subgraph. Take any click. No? That's it. So there is a gap between the degree and the connectivity. So what are we doing now? We say, oh, minimum degree and the connectivity, they may not be tied like this, but if I separate some gap, then we are able to tie them up with each other, right? So in the click example, if I said you, why, oh, this is not highly connected. Yes, in total this is not highly connected, but it does contain a n connected subgraph, induced subgraph, one of the clicks, right? Now, if I would have taken his proof, then what have I done? Oh, I find this separation, let's move to this side or that side, because one of the side I must go, right? Now, how can I keep going? I keep going, density increasing, I keep going, and I keep going in one direction. It is not possible, no? Graph is finite, right? You get my point? So like what I'm saying, I started with an assertion that this graph has large minimum degree or large average degree. I find a piece of the graph which still has a large average degree. I keep going. I keep finding the separation. I keep finding the separation. But every time you find a separation, it tells you to go somewhere, no? But it's a finite graph, no? So it should stop somewhere, no? And that's it. So now does the proof becomes intuitive, right? So what is an intuitive proof? Proof is very simple. You think about it. Okay, is my graph has a property? No. It means I find a separation and I move one direction, and it is exactly same as the graph I started, but I lost some vertices. Okay, let's do it again. Let's repeat this process. Oh, either this is the case or I found a piece to move, but every time you piece, you're losing something, right? But so look at the last stage when that happened. What are you saying? I still found a separator and this other side is very dense. Not possible, no? So somewhere you would have found it. So this is an intuitive idea. And rest everything is made to make the proof formal, right? Now, if I wanted to implement this idea, how will I implement this idea, right? First, I will get rid of small average degree vertices, okay? If I find a separator, I will say, okay, if I find a separator with both sides big and high average degree, I say, oh, by induction hypothesis, we will be done there. That's, oh, I am not done. Why? Because this is also small, that is small. Now you have to do something. But then, how can the whole graph has lots of edges and two induced subgraph can have small number of edges? Not possible, no? Right? So, but when I do a separate, and why separator are great to reduce the number of edges? Because whenever you have a small separator, these kind of edges are not allowed. So you reduce the number of edges that can be possible, go from a big side to the chunk side. So separator is a great way to reduce the number of edges. So if I find too many times, I will reduce lots of edges, no? But I started with too many edges, right? So think of this way, the separator also provides a way to not have edges between this side and that side. So the only edges which are possible is here and here, right? So that's an intuition that we have tried to make the proof go through. Okay, I think 11:11 is the right time to stop.